All right, so up next we have OuldRouis from Boston University.
Thank you. Hi, everyone. I'm OuldRouis. I'm a PhD student at Boston University. First, I'd like to thank the organizers. I'm really excited to be here. It's been a really inspiring conference, and I'm really excited to tell you a little bit about how white dwarfs can help us constrain remnant planetary systems as a function of mass. This work was published last year in AppJ and couldn't have been possible without all the people listed on the screen. All right, so all of you here know that our galaxy is full of exoplanets. The NASA archive can count almost 6,000 planets as of this year. And when we look at them as a function of mass, the story is a little bit different. There actually only has 2 confirmed exoplanets with masses above 3.5 solar masses. It's them right here. So we don't really know much about the more massive side of our galaxy and planets in those ranges. And that is mainly due to sensitivity biases of traditional exoplanet detection methods. And so we can actually look further in stellar evolution by using white dwarfs. Because planets at white orbits can actually survive stellar evolution. As the star radius increase, we think that most of the close-in exoplanets will get engulfed, and there might be some collisions as the orbits expand, but some planets do survive. And we can look for those planets and infer them with metal pollution around white dwarfs. I'm going to give you the punchline right away, and then we'll go into how I got there a little bit later. White dwarfs give us insight on remnant planetary systems. Actually, more than 40% of white dwarfs are metal polluted. This is the distribution of metal-polluted white dwarfs as a function of mass, where I have the white dwarf mass at the top axis and the progenitor mass, or main sequence mass, at the bottom. And you can see here that as the mass of the white dwarf increases, the fraction of metal-polluted white dwarfs slightly drops, with only 11% of massive white dwarfs that originate from progenitors 3.5 solar masses and up are metal-polluted. So this is still really exciting because planets around white dwarfs are common. But there seems to be a decrease for massive white dwarfs. So now let's backtrack a little bit. When I say metal pollution, I mean the accretion of scattered, tidally disrupted planetesimals onto the white dwarf. The strong surface gravity of white dwarf make it that any heavy elements like iron, silicon, calcium will sink past the photosphere on really short timescales. So we detect photospheric elements in the atmospheres of white dwarfs, and that tells us that there is remnant planetary systems. The accretion models actually implies 1 surviving planet and a modest reservoir of planetesimals. This is a figure from Eric Dennehy that shows you the sort of dynamical scattering that goes into tidal disruption and finally accretion onto the white dwarf. Interestingly, and you've heard a little bit about this from Laura Rogers earlier this week, the abundances that we find on white dwarfs are like bulk Earth with rocky elements like iron, oxygen, magnesium, etc. And so in the optical, we look at calcium very often, and in the UV, we look at silicon. So in practice, we can look for silicon in UV spectra of white dwarfs and infer metal pollution. What I'm showing here is 2 small white dwarf spectra from a sample of Hubble Space Telescope COS that the top panel here shows no metal pollution, and the bottom panel shows metal pollution. We can detect silicon to a limit of 10 to the 5th grams per second, assuming bulk Earth abundances, which I like to say is like 1 baby elephant per second falling onto the white dwarf. And if you're still not convinced that the bottom panel is metal polluted and the top is not, that might be because of this line that is actually interstellar medium contamination. And we know this from looking at the gravitational redshift of the white dwarfs. Okay. So in 2014, Detlef Koster, along with Boris Gensiker and Jay Faree, conducted a study on 85 white dwarfs, looking for the fraction of metal-polluted white dwarfs out of bright, young, and hot white dwarfs. These are the parameters of their sample, and the dark histogram shows what fraction showed metal pollution. And I've been really lucky to work with this sample that now counts 258 white dwarfs. And these are the same parameters for my sample. The orange histogram shows where I find metal pollution, and I want to guide you through those parameters slightly. Effective temperature, surface gravity, which helps us infer the white dwarf mass and the cooling age. In this temperature range, convection has not kicked in yet. So we don't expect heavy elements from deeper layers to be dredged up back to the surface of white dwarfs. And you can see the results I already spoiled at the beginning, that it seems like massive white dwarfs are less frequently metal polluted compared to average mass white dwarfs at 0.6 solar masses. But there could be another mechanism at play that would prevent us from seeing metals in the atmospheres of our massive white dwarfs, and that is radiative levitation. Radiative levitation can prevent metals from sinking out and sort of counteracting gravitational settling. We have some models for how radiative levitation is supposed to act as a function of elements, surface gravity, and effective temperature. Here I'm showing what would be an average mass white dwarf, log G8, which corresponds to 0.6 solar mass. And I'm showing the equilibrium abundance of silicon as a function of effective temperature. The white dwarf cools to the left. To guide you through plots like this, basically, a surface gravity of log G8 in this case, if we detect an abundance above the line, that would mean that it is actively accreted onto the white dwarf. But if we detect an abundance under the line, then that would mean that it could have accreted some time ago and still be supported for longer than what diffusion timescales predict. In this case and in this temperature range, diffusion timescales are really short, in the order of days to weeks. So this could prevent us from detecting metals onto the surface gravities, heavier surface gravities, which corresponds to more massive white dwarfs. What we at least know is that there was some time in the recent past where no abundance was able to be supported only by radiative levitation. So any metals detected on the photospheres of the white dwarfs would have been accreted some time ago. Because this has a strong dependence to surface gravity, it tells us that we might be preventing the detection of metals onto the more massive white dwarfs, which have stronger surface gravities. Thankfully, it is dependent on the element as well. And here I'm showing the radiative levitation models for silicon and for carbon. Carbon is less efficient to radiative levitation effects. And we find a temperature range in which no radiative levitation can support elements for carbon. And so this helps us define an active accretion sample. With this active accretion subset, we can compare apples to apples across the full mass range. So we can compare the more massive white dwarfs that are actively accreted with a lower mass sample that is also actively accreting onto the white dwarf. And this is what we get. Now we can compare active accretion onto white dwarfs, and we still find a rapid decline of massive white dwarfs being metal polluted. There's actually a 4 sigma difference between the white dwarfs with progenitor mass under 2.5 solar masses and the progenitor mass above 3.5 solar masses. So naturally, we now wonder why there would be missing signs of planets around massive white dwarfs. And one of the things we've looked at is if mergers would be to blame. Massive white dwarfs are expected to originate from stellar mergers more often than not. About 40% of massive white dwarfs could originate from mergers. And we can detect merger remnants among white dwarf with a couple factors like strong magnetism, rapid rotation, and atypical kinematics. So we looked at our sample of massive white dwarfs to see if mergers could be the cause for the lack of massive white dwarfs metal polluted. In terms of strong magnetism, we can detect magnetic fields with strength above 2 megagauss in white dwarfs. And in this case, our sample was selected against magnetic white dwarfs, and we don't find Zeeman splitting in the spectra. So that is probably not at play. In terms of rapid rotation, we look through tests, and we don't find variable candidates at short periods. So we don't think that there is a high fraction of rapidly rotating white dwarfs in our sample. And finally, in terms of atypical kinematics, there is an age-velocity relation for white dwarfs. Massive white dwarfs are expected to be young and therefore have slow transverse velocities. We can compare expected transverse velocities with measured transverse velocities from Gaia proper motions. This is what I'm showing here in galactic coordinates, VL and VB. The histogram shows the observed kinematics, so the observed transverse velocities from Gaia proper motions, and I have 2 different curves. The purple one is assuming single star evolution with 0% mergers, and the orange line shows you a 50% merger fraction. Kinematic outliers would be representatives of merger remnants among the sample. But we don't see high contamination of mergers in this case either. So based on our three factors, it doesn't seem that merger plays a significant role in the massive white dwarfs and cannot explain the lack of planets. So now we turn to planetary formation, architecture, survival, with a lot of hypotheses and not real answers. In terms of formation, we think that massive stars have more massive disks that may dissipate faster. That might mean that there is a smaller reservoir of planetesimals and debris to scatter in the white dwarf. In terms of architecture, the two planets that we know around massive stars are at really wide orbits. They're both at 300 plus AUs from their host star. If that is the case for all massive stars, then the scattering processes may be less frequent around massive white dwarfs. And that might be why we don't see metals as often. Finally, in terms of survival, mass loss processes are more extreme for massive stars. They lose more mass faster. Additionally, critical engulfment distances increase with mass. There might be a narrower parameter space for surviving stable planets. Those are all hypotheses, and we don't really know what's happening. And as often, we need more larger sets of data to increase our statistics. So one thing we've done, and that we're doing now, is look at Gaia, low-resolution spectroscopy, that could give us large samples of massive metal-polluted white dwarfs to investigate. We've done a spectroscopic follow-up of a few massive metal-polluted white dwarfs that have been identified with low-resolution spectra. I'm showing here what the Gaia XP spectra looks like, and then what our follow-up looks like from the Lowell Discovery Telescope, the Venice spectrograph. The spectral type with Gaia low-resolution spectra was identified with machine learning spectral type identification, and we actually find that most massive white dwarfs with a probability of metal-polluted above 50% do actually show calcium H and K and are actually metal-polluted. So this sample might be really helpful to find out more about missing planets around massive white dwarfs. I hope that I've been able to show you how exciting finding planets around white dwarfs is and all the possibilities of science we can do here. So I'll leave my conclusions here, and I'm happy to take any questions.
On the right.
Hi, thank you for this really interesting talk. Do you think if you plotted like the cooling time of the white dwarfs on a plot like this, it would look the same from what you're saying about the mass-age relation?
Right, so these are all really young stars in this sample. We're using really, can I do this? We're using a sample of really young stars so that we can compare active accretion onto a really homogeneous sample. Accretion is not expected to slow down with age. We find metal pollution for white dwarfs across the full cooling timescales. So that may be the same, but unfortunately convection starts playing a role around 13,000 Kelvin and down. And so that might dredge up metals from deeper layers, so it's harder to say whether the star is actively accreting or not. So it's harder to compare across a level of masses.
Cool, okay, thanks.
There's a question at the front.
This is really exciting stuff, great work. You mentioned that you check the rotation curves with TESS, and I'm wondering what our sensitivity with that is, because if we're kind of expecting that white dwarfs are basically just hot balls, then like what sorts of signatures would we expect to see in rotation curves from TESS?
Yeah, so we find a lot of transiting debris around white dwarfs with TESS. That's been really exciting work that has been done, and that was even used to find planets around white dwarfs recently. Andrew Vanderberg has done a lot of work on that. Rotation around white dwarfs, we think fast rotation, rapid rotation would be around a day.
But like what sorts of amplitudes would you expect?
What sorts of amplitudes?
Yeah.
Our detection threshold is like 5 times the median amplitude. It's like a 0.25%. I'm not sure how it compares to regular stars, I guess.
Gotcha.
Yeah.
Okay. Maybe I'll ask you about this in more
Okay.
detail.
That was a really enjoyable talk, thanks. So you might not be able to answer this, but I'm curious about the frequency of the white dwarfs that you're finding with the metals and how that implies the frequency that they hollow planets in comparison to all the work that was done on the K giants that were expected to be retired A stars, and they've looked for planets, right? They're supposedly, at some level the same, different ends of parts of the evolutionary track, but they should have similar recurrence rates, or whatever the right phrase is.
Yeah, we've looked at retired A stars quite a bit for this work. The constraints are a little bit different, but they seem to agree. The problem with previous to A stars is that all the planets we know right now are all going to be engulfed, probably, most of them. So it's really hard to compare to sort of previous stages of stellar evolution.
Fair enough, thanks.
All right, let's thank Lou again.